Our next presenter is Mr. David McGaw, N1 HAC, who will be talking to us about broadband loop antennas and preamplifiers for receiving VLF and receiving VLF to HF.
Oh, good morning. I'm David McGaw, N1HAC. I've been a research engineer at Dartmouth College for some time now, working under Jim LaBelle, and I'm vice president of the Twin State Radio Club in New Hampshire and Vermont. And this is mostly the work of Mike Trimpe, who I call our research engineer emeritus, who has set up and designed the antennas and preamps to a large extent that we've been using for the ongoing ionospheric research. I'll present some of the antennas that we've been using, various sizes, all similar design, but different sizes for different applications. Some of the theory that Mike has worked up, and then some on the preamp design itself. This is our standard, what we consider our standard antenna. It's about 10 foot on a side, 12 gauge insulated wire on a 17 and a half foot mast. Most of them that we've put up have been using TV mast, steel mast, 1 1/4 inch, nice and rugged, and is a convenient basis to build this. And you can see in the picture here, we put a preamp case down at the bottom of it. And in some of our cases, we do have polar bears and other critters vandalizing our antennas. That would be, the polar bear I think is primarily up in Churchill, Manitoba. But we've used these all over. This is one actually in place in Greenland. Unfortunately not there anymore. The original installation was some years ago, an array of 17 of these as an interferometer array called Canopus. More recently it had been reduced to 5. There was 1 reference antenna, 2 at 50 meters, and 2 at, I think it was 500 meters. The higher frequencies would use the inner array. Lower frequencies, we could go down to 100 kilohertz. Would use the further out ones. Recently, they pulled out the Sonderstrom ionospheric research facility, so we're not there anymore. This is the original antenna that we developed our AM Doppler system in, which picks up Doppler shifts on AM broadcast around the Northeast. This was a 2/3 size antenna, 5 meters squared. But we have found since then that we can use a much smaller antenna, much more convenient to put out in the field. So this is the one that we use now. It's much smaller, less than 2/10 of a meter square. It's about 1.5 foot on a side, 2-turn loop, which actually has the same very similar inductance to the big loop, but it's much smaller. And we have these deployed out in the around the Northeast, and have been picking up transient ionospheric disturbances, traveling waves around the Northeast, and we're thinking of building some more of these systems and putting them further out around the country. You'll notice on the one to the right that there is a GPS antenna also on there. Because of the nature of the level of Doppler shift, the systems are GPS locked. So we have the GPS antenna on the same mast. This is one that we have in Tulik. We had one of these in Greenland, and there is a conjugate one down at South Pole. This is a crossed loop antenna being used to detect the polarization of high frequency auroral roars. There's the fundamental aurora roar, which is something that Jim studies a lot, is at twice the electron cyclotron frequency up in the aurora. And through nonlinear mechanisms, it generates a second harmonic, which is fairly easy to see, and the standard antenna has been used for that. But that one of the characteristics of a loop antenna is that they're kind of well behaved up to about 0.085 wavelength. There's a treatment of that in the ARL antenna book on small loops. But above that, it isn't, the idea is that the wave is equal at all portions of the wire. Above that, the inductance starts getting different. The impedance starts increasing. And of course, eventually you get to a half-wave loop, which is high impedance. Full-wave loop was a completely different animal. So we reduced the size of this because we were looking for things up towards 10 megahertz instead of 5 megahertz. The standard antenna meets that wavelength criterion up to about 2 megahertz, and then it's useful to 5, we've found. This is, we've got a system that we're looking more in the 5 to 10 megahertz for higher frequency roars, and have in fact seen them both at Tulik and South Pole. So that's a half-size loop that we have. And this is the one that we have down at South Pole. It was installed 2015, I think, thereabouts. South Pole, it doesn't snow, but it does blow. And from the previous, the picture on the top is what we were just recently sent. They were trying to figure out whose antenna is this, and I said, that's ours. The one in the front is actually one of the original 10 meter squared antennas that we had put in down in South Pole on a wooden frame before it was being done with the antenna mast. And so we recently put in this HF polarization antenna, and because cables are hard to come by down there, we actually took the cable from that first antenna and put it over to the second one. And so just in a few years, the preamp case and the bottom of the antenna have become covered over. This is why they built the new station on telescoping legs, because the snow blows in and it does accumulate like 6 inches a year. So you have to account for that. But as it turns out, snow is a good insulator, and we have antennas that are pretty much buried, but they're still effective creating good data. This is also at South Pole. This is a double-size antenna that we developed. We put in, that's about a 50-foot mast, 20 foot on a side on the loop. Also crossed loops because this was to look at polarization of AKR, auroral kilometric radiation, which is in the 500 kilohertz to maybe a megahertz or above range. And it's also a very weak signal. It's something that isn't really supposed to be coming down. So we built a system that is particularly sensitive for that frequency range. So that's the range that we have developed. Everything from the small AM receiver to this very large one intended for very weak signals. Mike worked up this document on the design and analysis some years ago. And this actually appears as an appendix in Eric Nichols' book on receiving antennas that came out recently. But I do also have the original document if anybody's interested. I know this is a lot on here. I just wanted to present it and have it show that it's available. He talks about how the voltage is induced in the loop, and then the strength of the actual signal, and the analysis of how it is that these work well over broad frequencies. You have the inductance of the antenna. It's working into a load resistance, and over a broad range of frequency, the induced signal follows the increased impedance of the inductance. So it actually ends up giving you a very constant signal over a wide range. And then the inductance at the low end has it roll off, and then the capacitance that you see as the input impedance, part of the input impedance of the amplifier, gives you a high frequency roll off. And this is showing that in our amplifiers, we usually use a transformer because the input impedance is usually up in the kilo range, but the antenna is more down in the tens of ohms range. So you want to match that to maximize your signal sensitivity. And I went the wrong way. There we go. And then we've set up a simple calibration system that works against that impedance and allows us to actually, in the lab or also out in the field, put in a calibration signal and make sure that the bandpass of the system is what we expect it to be. And then also looking at the minimum detectable signal, doing your noise analysis, figuring out what's the signal going to be, what's the noise in the system going to be. This is very close to what we've used as our standard amplifier out in the field. It's a little bit different, but the analysis is valid. And this is the architecture that we use. And shows the inductance of the antenna, goes into the transformer, and then it's actually a dual feedback system in that each of the two amplifier stages has local feedback to set its gain, and then our feedback that's shown here is actually to set the input impedance that the antenna is seeing. Mike worked out that using a feedback resistor like that, rather than having a resistor at the front end, is actually much lower noise. So it contributes less to the noise of the system than the way other systems are often designed. So this gives you the minimum detectable signal. and the response of this particular system. And this is a view of the preamp that we generally use. It's a single preamp, gets put in a case with a little bit of insulation, closed up, and then put out in the field, either in a case. And there are places, we just, if it's just going to be snow, like in Antarctica, it'll just be allowed to get buried in the snow. This is the AM Doppler version that we use, and this one shows, this is probably the most narrow band that we do. The one that is used on that very large loop in Antarctica would be similar in its limited frequency range, but you can design it so that it's relatively tight. We just want to, for this, we wanted to pick up essentially the AM broadcast band, which is from about 500 kilohertz to 1600 kilohertz. So this is a low gain one, and it gives about a voltage gain of 100 through the system from antenna to output. And it's been tailored for this particular response. Now, this is what I call the standard mic preamp. This is what we mostly will use on our standard 10 meter square meter antennas. Gives about, intended response is 100 kilohertz to about 4 megahertz. And then gives about 500 voltage gain. And then this is the preamp that's been developed for the small loop, which gives a much wider range. We actually roll it off down at the low end because we're not interested in that. This was for the higher order aurora roars, the harmonics of that ion cyclotron frequency. So this gets up into the 9 megahertz range. And again, gives about probably 500 gain. So very high gain, actually. And I'll make a note that there are other broadband loop antennas out there on the market. Their amplifiers, one, are noisy, and two, are not very high gain. I was measuring one that had a gain about 25 dB. This is much higher than that. That's about a gain 10 to 12. So we also, I will note, out in the field, we have these very weak signals that we're picking up, and also very strong signals right nearby, because there are non-directional beacons down in the LF range. There are actual AM broadcast stations in some of the sites that we have that are right nearby, and they can be up to like 6 kilohertz. We're trying to site something right now that one of the possible sites has a 6 kilowatt non-directional beacon within a mile of where we're wanting to put this. So I have developed notch filters for both in front of and behind so that we don't overload. So this is, we also have a dual preamp. This is the one that was built for that very large antenna. And then this is another version of it in process. There are other pieces that get put on that will actually do phasing and combining so that we can get both polarizations out of a single cable, switched back and forth, so that when we're limited to one cable, we can actually get polarization information out. And finally, this is our latest incarnation. It's a telescoping mast that for our standard size antenna that we're hoping to site up at Baffin Island, which turns out to be conjugate to South Pole. So there are reasons to put things at either end of the magnetic lines and see what bounces back and forth. So that's my presentation.
Okay, so we're going to move on to the next speaker.